Hello, I'm Miss Igo. Welcome to my classroom. In this video, we're going to be talking about factoring the difference of perfect squares. In order to use the factoring rule, difference of perfect squares, there's some criteria that has to be met first. First of all, the word difference in math means subtraction. So, in order to factor a difference of perfect squares, we have to have a binomial, meaning we have to have a polynomial with two terms, and those two terms have to be subtracted. It's a difference of perfect squares. Also, every number and every variable in the polynomial has to be a perfect square. Perfect square numbers are numbers that we can get by multiplying another number times itself. For example, 4 is a perfect square because 2 times 2 equals 4. 25 is a perfect square because 5 times 5 is 25. Variables are perfect squares when the exponent is even. So as long as we have a binomial, so in this first example, then we have a binomial, meaning we have two terms. There's two terms. They have to be subtracted. So this sign here in the middle has to be a minus because they have to be subtracted. That's the difference of perfect squares. And every term has to be a perfect square. 4 is a perfect square because 2 times 2 is 4. And x squared is a perfect square because the exponent is an even number. So x squared is a perfect square, x to the fourth is a perfect square, and so on. As long as the criteria is met, we can factor using the factoring rule difference of perfect squares. And this is a very easy method of factoring. To factor using the factoring rule difference of perfect squares, our result is going to be two binomials. So I'm going to go ahead and write two sets of parentheses because I'm going to fill this in with two binomials. And all we have to do is take the square root of each part of our binomial. The square root of x squared is x. So the square root of a number is when we ask ourselves, okay, what number could we multiply times itself to get that number? If I were to multiply x times x, I would get x squared. So that means x is the square root of x squared. What is the square root of 4? The square root of 4 is 2 because 2 times 2 is 4. Anytime I take the square root of something, I'm asking myself, what could I multiply times itself to get that number? Okay, so now that I've taken the square root of each part and written it twice, my signs that are going to go in my binomials, I just have to put one of each sign. So plus and minus. Or I could have written x minus 2 times x plus 2. It doesn't matter what order you put the group in, but the stuff inside needs to be like, here, this is x minus 2, here's x minus 2, x plus 2, x plus 2, but it doesn't matter what order the group is in. All right, this one is similar to the first one. Again, we have to make sure that we have a binomial, that's two terms, and it's a difference, so subtraction in the middle, and every term is a perfect square. Well, we know that x squared is a perfect square, and 100 is also a perfect square because 10 times 10 equals 100. All right, so the square root of x squared is x. Put it in both spots. The square root of 100 is 10. And then one of each sign. So in the other example, I should have shown you how to prove to you that this is in fact the factored solution for our binomial. So remember, whenever you factor something, you should always be able to multiply your solution back together and get what you started with. So let me show you what would happen if we were to multiply these two binomials together. Anytime we have two binomials, we can multiply them back together by using FOIL. That's just a method to help us remember to distribute every term. So I multiply the first two terms together. X times x is x squared. The outer two terms together, that would give me a negative 10x. The inner two terms would be a positive 10x. And the last two terms of positive 10 times a negative 10 would be a negative 100. Well, if I combine my like terms, negative 10x and positive 10x, that would cancel each other out. And I'm left with x squared minus 100, which is what I started with. So remember, that's how you can always check when you factor, check to see if it's right by multiplying your solution back together and see if you get what you started with. So my solution here is the x plus 10 times x minus 10, or you can flip it and do x minus 10 times x plus 10. Here's another binomial. This time we have a coefficient other than 1 in front of the x squared. But as long as they're all perfect squares, we can still use the factoring rule, difference of perfect squares. Again, this is subtraction. 9 is a perfect square, x is a perfect square, 49 is a perfect square. So I'll do my two sets of parentheses. Take the square root of each part. The square root of 9 is 3. The square root of x squared is x. And the square root of 49 is 7. 1 plus and 1 minus, and we're done. Here we have 25 minus 36x squared. 25 is a perfect square, 36 is a perfect square, x is a perfect square, and they're being subtracted. So if I do my two sets of parentheses, the square root of 25 is 5. The square root of 36 is 6. And the square root of x squared is x. Plus and minus. So sometimes I'll see students say, okay, well, I don't like it like that. I want the x, the term with the x to go first. So they'll rewrite it like this. They'll say, okay, 6x plus 5 and 6x minus 5. But that would be incorrect, and let me show you why. If I were to multiply this back together, 6x, positive 6x times positive 6x would be a positive 36x squared. And then if I multiply my inner and outer terms, I would get a negative 30x and a positive 30x. And then my last two terms, my positive 5 and negative 5 would be a negative 25. So my two middle terms would cancel out, and I would get 36x squared minus 25. Is that what I started with? Even if I were to rearrange this, this is a negative 25 and a positive 36x squared. That's not the same as what I started with. I started with a positive 25, not a negative 25. I started with a negative 36. Negative 36x squared, not a positive 36x squared. So you can't just flip the stuff that's inside of the parentheses. Whatever came first needs to go first in your parentheses. Otherwise, your signs are going to be wrong. So this is incorrect. This would be the correct solution. Again, you could write it as 5 minus 6x first, and then 5 plus 6x, but you can't switch the terms inside the parentheses around. All right, here we have x squared plus 64. So this is a binomial. Can we do a difference of perfect squares? No, because this is not a difference. Remember, the middle term or the middle sign has to be a negative in order for it to be a difference of perfect squares. These are both perfect squares, but it's not a difference of perfect squares. So we cannot use difference of perfect squares. If we tried greatest common factor, they have no factors in common. So if there's no factors in common, we can't factor it, then we say that this is prime. It cannot be factored. In this binomial, we have a fraction, but as long as each part of the fraction is a perfect square and the rest of the criteria is met, we can still use difference of perfect squares. Well, 4 is a perfect square, 9 is a perfect square, x squared is a perfect squared, and it's a difference. So we can use difference of perfect squares. So I'm going to do my two sets of parentheses, take the square root of each part. The square root of x squared is x. The square root of 4 is 2, and the square root of 9 is 3. And then 1 plus and 1 minus. Now in this binomial, when I look to see if I can do difference of perfect squares, I see that I have a perfect square in x squared and a perfect square of y squared. It's a difference. However, the 3 and the 27 are not perfect squares. So before we give up on this binomial, let's see if there's a greatest common factor. 3 and 27 have a greatest common factor of 3. So I'm going to factor out a 3 first. So if I divide each term by 3, if I factor a 3 out, that leaves me with x squared. 27 or negative 27 divided by 3 would be a negative 9, and then I have the y squared. Now I have x squared is a perfect square, 9 is a perfect square, and y is a perfect square. So I do have a difference of perfect squares. So if I factored something out to begin with, that's just going to tag along with my answer. And then I'm going to factor the rest of it using a difference of perfect squares. So I take the square root of each part. The square root of x squared is x. The square root of 9 is 3. And the square root of y squared is y. 1 plus and 1 minus. And this whole thing would be my solution. In this last example, again, we don't have a difference of perfect squares to begin with. Now, a to the 4th is a perfect square because my exponent is even. But 6 is not a perfect square. Both terms have a 6, so let's factor that out of our binomial. That's going to leave us with a to the 4th minus 1 if I factored out a 6. So remember, when we're factoring, we're just dividing. So that left me with a to the 4th. 6 divided by 6 is 1, or negative 6 divided by 6 is negative 1. Now, this is a difference of perfect squares because a to the 4th is a perfect square because my exponent is even. And then 1 is a perfect square because 1 times 1 is 1. So as long as there's a number that I can multiply times itself to get that number, that means that number is a perfect square. So again, I'm going to bring down my 6, and then I'm going to factor this a to the 4th minus 1. Well, the term that I can multiply times itself to get a to the 4th would be a squared. A squared times a squared gives me a to the 4th. And 1 times 1 is 1. 1 plus and 1 minus. Okay, are we done? No, we're not done because we still have another difference of perfect squares. So we need to factor that. The terms that don't need to be factored, we're just going to bring down. So we have the 6, and then we have the a squared plus 1. We can't factor that using difference of perfect squares because they're being added. That's a plus in the middle, not a minus. But this a squared minus 1 can be factored again. The square root of a squared is a. The square root of 1 is 1. And 1 plus and 1 minus. And now it is completely factored, and this would be my solution. And that's how we factor using a difference of perfect squares. Thank you for watching.